Bienvenue tout le monde au séminaire de mathématiques physiques de cette semaine. Welcome everyone to the Math Physics seminar. Today, it's my pleasure to introduce Yuan Miao, who just a year ago finished his PhD at Amsterdam, working on integrable systems, and now moved on as a postdoctoral fellow at the Galilei Institute in Florence. And today he'll tell us about Baxterization, but with a Floquet twist on it. And this is work with Gritsev and Kurlov. So Yuan, please take the mic, and this is recorded. So I'm assuming you're fine with the recording.
Sure, no problem. Yeah. Okay, thank you very much, William, for introducing me, and also I would like to thank Luc for inviting me to give this talk here at this great seminar series. So today I'm going to talk about some recent work that I've been doing together with my collaborators Vladimir Gritsev from University of Amsterdam and Denis Kulov from Russian Quantum Center in Moscow. So today I will talk about so-called the Floquet Baxterisation, as I wrote here. Maybe it might be a little bit confusing to some of you, but hopefully in the next 1 hour I'll try to explain what exactly mean by those two objects. And today the main focus of today's talk is just to understand whether we can solve some out of equilibrium quantum system exactly using some techniques that we are familiar with from the integrable vertex models in statistical mechanics. Okay, just to begin with, I would like to give the outline of tonight's talk. First of all, I would like to motivate all of us why we're interested in out of equilibrium physics and integrable or exactly solvable models. And then I will introduce our out of equilibrium protocol, which is Floquet dynamics. And here I would like to basically to connect the Floquet dynamics that I consider with some very typical techniques to simulate quantum many-body systems. For example, the Trotterisation to study time evolution. And after that, I would like to explain some general constructions of some integrable Floquet dynamics just directly from Yang-Baxter equation that the integrable system satisfies. And after that, I would like to give some examples. For example, the simplest one is the 6-vertex model, also known as spin 1/2 XXZ chain, where we would have we can construct an exactly solvable model using the framework that we introduced before. And then there are some applications such as there is an anti-unitary symmetry breaking in the easy plane regime. And after that, I would like to conclude and give some outlook. So just to begin with, let's ask ourselves why we're interested in out of equilibrium physics. Well, first of all, out of equilibrium physics is really ubiquitous. It really appears everywhere. As a matter of fact, in my opinion, it's more universal than the equilibrium physics. For example, if you're an experimentalist, you're interested in studying, let's say, the dynamics of some, let's say, some quantum gas confined in a potential. When you turn off the potential, you want to understand, or in principle, you can change the potential. You want to understand how this quantum gas expands or evolves with time. And that's intrinsically an out of equilibrium problem. Or if you are more interested in not in the quantum world, but in more macroscopic objects, such as the galaxy or the universe in principle, well, the universe is expanding, so it's not in equilibrium. So in order to understand, let's say, some physics of the universe, well, we might start with trying to study some quantum many-body system as a toy model, just to understand whether there's some universality over there. And more importantly, there will be new physics of matters that do not exist in the equilibrium for non-equilibrium physics. The simplest example is the one that in classical physics, so-called Kapitsa's pendulum, as shown here. So the system that Kapitsa studied is that you have some pendulum, where you have some fixed point with some, let's say, some rigid body bar, let's say a wooden bar with some metal ball attached to it. Because of gravity, of course, without driving it, without any force in equilibrium, there's only one stable point, which is going down. However, if we start to drive this fixed point periodically in a very high frequency, in addition to this stable point, also the system can also be stable on top, even though the balls are wobbling. But still, this new, let's say, this new phase does not exist in the equilibrium without driving. So, two more, let's see, fashionable terms. There are many new things in quantum many-body physics that's unique in the out of equilibrium, such as dynamical phase transitions or time crystals that people have studied recently. And secondly, why we are interested in, let's say, integrable systems or exactly solvable models. Well, first of all, we have lots of access to some analytic results using the mathematics tools that we know, and this leads to exact or rigorous results that might not be possible for generic non-integrable systems. Moreover, the integrable systems, they are not agordic. For example, if we study a quantum quench, as we heard from last week's talk, there might be the absence of thermalization. And the reason is that there exists infinite many conserved charges that can be written in terms of local densities. So here I use the quotation mark here because in principle, there are also other charges that are not exactly local, but they're quasi-local, which also contribute enormously in the thermodynamic or hydrodynamic descriptions. Specifically, the model that I consider here, they satisfy the so-called Yuan-Baxter equation, which can be exemplified in this figure. You can think of it as in two ways. First of all, you can think of it as you have some quantum many-body system where there are some excitations or quasi-particles. So the scattering processes of those quasi-particles, they satisfy this factorization property that any three-body scattering can be factorized into two-body scattering. And basically, so there you can think of it as for each vertex, you can think of it as some kind of S matrices that's attached to it. But here I would like to think of it more from the statistical mechanics point of view, where these are kind of the basically so-called the R matrix that are basically associated to the Boltzmann weight of some vertex model. But the exact interpretation is not very important here. And basically, this diagram we can also write it in terms of this formula, where these R's are basically the so-called R matrix that's acting on the Hilbert space that's living on these vertices. Yeah. So basically, the one that I wrote here is not the generic form. You can see that here there are some parameter called the spectral parameter. That's any complex number. They are of difference form. So basically, so here is u minus v is basically u minus w minus v minus w. And this is a very special piece of the Yuan-Baxter equation. But just for the simplicity of today's talk, I will just stick with this one. But actually, the result that I will present actually is more general. It also works for the case when this property is not satisfied. So once we have these R matrices, we can construct something called the monodromy matrix, which is the product of lots of R matrices that's sharing some space called the auxiliary space. So basically, this will acting on in addition to all the physical Hilbert space of let's see of some quantum spins, and then there's some additional auxiliary space. But then in order to study basically the physical, let's say some physical quantities, we need to trace over this. So we take a partial trace over this auxiliary space. And if you're not familiar with this language, but you're rather familiar with, let's say, a tensor network, so this transfer matrix here is just some matrix product operator acting on some physical Hilbert space. And here, as you can see here, I add some kind of inhomogeneity for each lattice side. So these sides, they are also in principle just some complex number. And moreover, it in principle can be different for each lattice side, which will be important later. So once we have that, just by using the Yang-Baxter equation that I write down, we can show that this R matrix is an intertwiner between two monodromy matrices. So basically what it does is that if you're acting on this R matrix, you can basically exchange these two operators, even though these two operators, of course, they do not commute in general. But however, once you've done that and you trace over both auxiliary space, you can show that basically all the transform matrices are in evolution. So namely, they commute with each other for any even different spectral parameters. And in principle, these transform matrices, there are some polynomials in this parameter U. And we can, in principle, expand over this U at some value. For example, U equals 0. And we can take the log derivative to basically get, so these coefficients, they have to commute with each other. So this forms, like, let's say, infinite many commuting charges. That's basically how we can use it to study the thermodynamics of the integrable systems. So here, basically, in order to get the local one or quasi-local one, we need to put the homogeneity altogether to 0, which of course is not, which is not always the case that you want to consider. But if let's say we put all this psi m to 0, then we get this Qn, which sometimes can be written in terms of local operators. I will show you some examples later. And now let's take a step back. Let's think of what exactly the out of equilibrium protocols that we want to consider. So we want to consider the so-called Floquet protocol, where we consider a time-dependent Hamiltonian that evolves with time, where this h is periodic in time. So basically, this big T is the period, and so this Hamiltonian repeats itself. So in principle, for a time-dependent Schrodinger equation, we can write down the time-evolved quantum states as here. Well, it's a path-ordered integral over the time-dependent Hamiltonian. Since we know that this Hamiltonian is periodic in time, for any integer value of this period t, the quantum states can be written as nth power of some operator called the Floquet evolution operator UF. And moreover, we can define something called the Floquet Hamiltonian as some kind of effective Hamiltonian for this time evolution, where basically we can obtain it by just taking the logarithm of this evolution operator. So here I would like to just to stress here that this HF is not a real Hamiltonian, and the eigenvalues of this HF, they are not really on the real line, but instead they are basically compact because it's only defined up to the logarithm. So so basically it's defined up to 2 pi over t. But in principle, we consider any h that's kind of periodic. But let's focus on a very simple example where h is a step-like function. So here, this diagram, you shouldn't take it too seriously. So this is just for illustration. That this h for some time 0 to t1 is this operator h1, and between t1 and capital T is h2. So in this case, we can write down basically the Floquet evolution operator as just the product of these two exponential, even though it might not, so h1, h2 might not commute. So basically, this is still a very complicated object in principle. And moreover, okay, instead of doing this step-like protocol, you can also think of it as some kind of kicked Hamiltonian, which is equivalent to get the same evolution operator. But let's stick with this one for the simplicity. And here, what I would like to know is, for example, the spectrum of this operator, and moreover, whether I can write down some kind of analytic results for this Floquet Hamiltonian HF. And moreover, if you really look at basically the quantum states, and if we're only interested in the quantum states at basically at the integer values of this capital T, then we can think of this time evolution as some kind of a discrete time evolution, or in a sense, a stroboscopic evolution. And in this case, we can think of it as some kind of Trotterisation. So first, I'd like to, just to remind ourselves what is Trotterisation. So let's say we have some Hamiltonian that can be written as two parts, H1 and H2. And also let's assume that the H1, H2, they do not commute. And then the time evolution of this Hamiltonian can be written as basically two parts. But when this delta T is very small, infinitesimally small, but we involve with, let's say, n steps where n goes to infinity. So this has basically some arrow of order delta T squared. But here, okay, so let's say delta T goes to 0, then this becomes exact. And also but then the question is, what if, well, we don't consider delta T very small. We consider delta T is not small, but some order 1 value. In this case, well, of course, if delta T is not going to 0, this limit is not there, then this equation will not be satisfied. Instead, we can use the definition as we did before. So we can just say that there exists some Floquet Hamiltonian, basically equals to the product of these two operator, where this T1, T2 are kind of this kind of that delta T, which is of order 1. And moreover, if we really think about H1 plus H2 is some total Hamiltonian, and then H1, H2 can be written in terms of local terms. And so between all these H1s, all these local terms, they commute. So basically, if the interaction is only nearest neighbor, then we can think of it as H1 as sum over all the odd terms, and H2 as sum over all the even terms. And then they commute among themselves. Then this U1, U2 can be just written as product of some operator acting on basically either even or odd sides. And in this case, we can rewrite this this Floquet evolution operator as this kind of a quantum circuit. So that's basically so instead of studying the full Floquet Hamiltonian, we can just think of studying some discrete time evolution of this quantum operator. And then naturally we come to this question. So what if this H, which is the sum over H1, H2, is integrable? Does it guarantee that this HF is also integrable? Well, the answer is it's not guaranteed that it will work if you just naively do that. However, we can construct basically this integrable Floquet Hamiltonian from the Yang-Baxter equation that I introduced before. So in the rest of my talk, I assume these two properties. First of all is that I define something called R check, which is R multiplied by permutation operator. So permutation operator, what it does is PAB acting as some operator OA is just OB PAB. And moreover, I assume that this R matrix at let's say spectral parameter U goes to 0 is just permutation operator. But of course, not all the R matrices that satisfy Yang-Baxter equation satisfy this property. And maybe later when we finish our paper, you will see that we can actually prove some general statement, not really using this assumption. So basically, just for the simplicity of this talk, let's assume that it's true. So then we have this. We define this object, so-called the Floquet evolution operator. That's basically in this form, where this O now is just this R check, product of this R check. And I see that it is integrable. Namely, I can write this UF as basically in terms of some transfer matrices. And where these transfer matrices are basically this inhomogeneous transfer matrix that I introduced before, where the inhomogeneity is put in a staggered way. So basically, for the odd side, it is let's say the inhomogeneity is 0 and all the even side inhomogeneity is minus alpha, where alpha is in principle is just some complex number. And this
is the Hamiltonian H now one of the conserved charges you're supposed to be able to construct from this R matrix directly?
Yes. So basically, we can get H from the homogeneous transform matrix. However, here you see that this I will not prove it, but you can see that from here this transform matrix is defined on an inhomogeneous transform matrix. So basically, these objects do not commute with H. If you think of H as the conserved charges from the homogeneous transform matrix. I will show you an example later for the 6 vertex model. Maybe this will be clear later. So so basically the point is this UF will not commute with something like H, but it commutes with so this HF also does not commute with H. And this procedure, I call it a Baxterisation, because I start with something that do not have a spectral parameter. So it's just some, some kind of partition function, or some, just some transform matrix, but without any spectral parameter. But once I identify it with the transform matrix of these staggered transform matrices, then I can associate spectral parameter. Here, this 0, of course, can be anything else that commutes with this UF. And this procedure, I would like to call it Baxterisation. And moreover, this G here is this product of permutation operator. So basically, what it does is it translates operator. So basically, if I act on G, so G acting on operator OM is OM plus 1 G. Yeah. So basically, it's a translation operator. But here, as you can see, that we have a staggered transform matrices. So we have G squared, which so G does not commute with this T, but G squared, since it's translated by 2 sides, it commutes. And actually, without really proving it using algebra, we can draw some diagrams. And here, the rules are basically the permutation operator is just some delta, just some product of some deltas, where basically I can write this delta AD as just a line, and also delta BC as a line. So basically, so that's how I write all these, all these objects. And also I use the property that I show it here. So R0 is permutation. So that's why here is all just permutation operator. And when it's not permutation operator, I write it as like a cross with some angle, where this angle is the spectral parameter that I denote. And you can easily see that if you just follow, let's say follow this one, it interacts with this one, and then it goes around, interacts with the other one, and goes out as here. So this is equivalent to see that this goes here, and then it goes out at here. So you see that it goes out the second to the right. So this basically denotes this light cone. And in addition, if you consider this one, well, it's the same. This is 1 interaction, 2 interaction, and then goes out here at the fourth. So this one is here. So basically our UF of alpha is this one. It's equals to this object, and this object we can rewrite it dealing carefully with the indices. We can write it as a quantum circuit. Basically, this can be considered as kind of a graphic proof of the statement that I write down. And this is really great because, okay, so before we discussing the physical property, I would like to make some remarks here. So first of all, this proof that, or the proof that I showed you is very generic. So I didn't assume anything. There's no requirement on the representation, both on the physical and the auxiliary space. So in principle, as long as these two are the same, we can basically construct this Floquet evolution operator that can be expressed in terms of the staggered transform matrices. For example, if you like a spin 1/2, you can get, you start with the 6 vertex model, you get some kind of XXZ like, so of course it does not commute with XX Hamiltonian, but it looks like some XXZ quantum circuit. But in the meantime, you can also choose a different representation. You can choose the spin 1 representation, where you can get this homological Floquet model, which like model, which is of course has a bit which is a bit different from XXZ. And moreover, this is about the unnested system. So it's about basically about the algebra of UQSL2, where this is and it's not nested system. But if you like, you can also study the nested system. You can study a SUN, basically R matrix, or even UQSUN or SO2N, whatever you like. This construction works. So basically, we will get a Floquet, let's say, quantum circuit using this construction. And moreover, here to show you, just for the simplicity, assume there's the regularity condition, which means this R at 0 proportional to permutation, but this is actually not important. And moreover, I also assumed the R matrix of difference form. So basically, in principle, this R matrix can be read as this instead of not necessarily equals to U minus V. But if you don't assume that, the proof in algebra it's more or less similar, but we can also prove that. So basically, what I showed you is a general framework for constructing Floquet integrable systems from any Young vector equation. And this already has been considered in the literature. First in the 90s, so-called, they call it light cone Bethe-Andreas, because here it looks like some kind of light cone, by basically some works by Destry and De Vega. Also, more recently, it has been studied by Leonard Zlatnik and his collaborators. They call it integrable Trotterisation, as well as by some work by Peter Claes and his collaborators. And moreover, here, since we can write down basically this UF, this Floquet evolution operator, in terms of the transfer matrices, so the Floquet Hamiltonian is just the logarithm of it. And basically, you can write it basically as the logarithm of this transfer matrices, which I show you is some MPO. And here, okay, this so there's some G squared, and this is related to the physical momentum of a staggered system. So in principle, however, in principle, this Floquet Hamiltonian is non-local. So it's not like, so it's effective Hamiltonian. It's not like, even though we start with some circuits that's strictly speaking local, but the Floquet Hamiltonian itself is in principle quite non-local, and it's very difficult to express it in terms of local operators, even though this is already a very nice compact way to write down this analytic expression for the Floquet Hamiltonian. Yeah, so basically there are very rare results about exact exact expression for this Floquet Hamiltonian, except for, let's say, for the free system or or spin system that can be transformed into a free fermion. And moreover, here you see that I'm using alpha instead of t before, and turns out that this alpha is, it can be expressed as a function of this period t, as I will show you in the example later. And what I showed you is that this Floquet Hamiltonian is related to this transfer matrix, and this transfer matrix commute with basically a staggered transfer matrix with any u, which is a complex number, and then all the log derivatives of these staggered transfer matrices, it also commutes with this Floquet Hamiltonian, and that's why that's what we call it integrable. And this first has been studied by my collaborator Vladimir, and also there's some recent work by Vladimir and Denise about basically the discussion about this framework. And here, okay, I'm cheating a little bit, because now in order to get the local concept charges, we cannot just take the log derivative at the spectral parameter u goes to 0, but we have to add another one to make it local. But this is not very, this is just the fact that we are considering staggered inhomogeneities. But I will not spend too much time on this. It's not very important. Yes.
Excuse me. Do you think that this Floquet Hamiltonian could be quasi-local?
Okay. So that's a very good question. Actually, as I will show to you, maybe it will be a little bit clear later. Some operators are kind of more, so for different value of alpha, this operator can look a bit local. So in principle, you can make it, I am not entirely sure that it is quasi-local, but it can be, some of this alpha value can be more local than the others. So maybe when this alpha, when you take some extreme value, such as infinity, maybe this HF will be either local or quasi-local. So that's, yeah. Also, actually, in the example of six-vertex model, when you take this alpha to infinity, it's also related to the dual unitary circuits that people consider. Maybe there, actually, you can get a relatively local, yeah, Floquet Hamiltonian. But if you choose, let's see, arbitrary alpha, which is especially small alpha, the expansion is actually goes, even this non-local term contains more weight. So it's in a sense very non-local. But maybe it will be more clear in an example later. Yeah. Thanks. Okay, thanks for your question. Okay. So let us proceed to the example that I want to discuss. So basically, this is an example of six-vertex model. So of course, there are many ways to actually write down a six-vertex model. Many ways to write down the R matrix. I'm choosing the way that's a little bit better if you think of it more from a quantum group point of view. So I consider basically this R or R check, which is, as I just remind you, is R product by permutation operator, is identity minus something which is called EM. And here you see that it's like in the endomorphism of two. So basically, it's acting on C2 tensor L, where L is number of sites. So it's acting on the endomorphism of that Hilbert space, and it's acting non-locally on two sites. Where if you write it out, write out the basically the representation explicitly, then it looks like this. So here is 1, and here it's some function of this U. So if you parameterize by this, then it satisfies basically this. So it satisfies this kind of RAB, RAC, U minus W, etc. So this is of difference form. Of course, you can parameterize it using different ways. Then it satisfies maybe different Yang-Baxter relation. But here is the one that is more useful for me. And this EM actually satisfies this algebra called affine template-Lieb algebra. So I consider periodic boundary condition. That's why it's affine. And basically, the most important property is that EM squared is just proportion to EM, where this beta is related to this parameter eta here. So eta is a complex number in principle related to the model itself. Also, it has some kind of a braiding relation here. And if you want, you can write down this EM in terms of the local spin 1/2 operator. And here you can see that it's something like sigma x, sigma y, sigma y plus something I call it delta, sigma z, sigma z. But here we have to be very careful because, well, it contains this term. Well, this term you can see that it's kind of a boundary magnetic field. And moreover, if this eta is real, of course, there's no problem. It's just adding a real magnetic field on like different magnetic field on each on the neighboring site. But if eta is let's see purely imaginary, then this sinh eta is also purely imaginary. Then it's basically like we are acting some imaginary magnetic field on the neighboring spins. And this will be important why we will end up with a kind of a non-Hermitian Floquet Hamiltonian. And there we can really study the anti-unitary symmetry breaking, as I will show you later. So this model, you can solve it using Baxter. I will not, bore you with the technicality, but this is actually the whole point why we can get lots of nice results of this model. and you can find more results, more technical results from our paper, which should be out soon. So if we consider homogeneous transformatory, just as the question asked before, well, we end up with this very nice Hamiltonian called XXZ Hamiltonian, which is you can think of it as just sum over this Template-Lieb generators. However, here you see that even though we have this term, which is some kind of a boundary magnetic field term, but if we are having a periodic boundary condition, all these things cancelled in this Hamiltonian. So if you just look at this Hamiltonian, you might see that, okay, this term is actually irrelevant. However, if you write it as H1 plus H2, where H1 is the sum over the even operator and H2 is sum over the odd one, then of course for H1, H2, this term do not cancel at all. Actually, this term present for all the H1 and H2 here, and this is also why I want to tell you that okay, in principle this thing can be imaginary, which is important for later. Okay, so if we define some basically some Floquet evolution operator just as exponential of H1 and H2, since H1 H2 consists of terms that commute, so basically for okay, here I forgot to write that EM commute with EM plus N, where basically N is larger than 2. And so basically all the terms here among themselves, they commute with each other. And then in this case, we can write this as exponential of this operator here. Even though these two parts, they do not commute, because H1, H2, they don't commute. And actually, we can rewrite this exponential using the property that E squared is basically E, proportional to E. We realize that this is nothing but a R check. And as I just showed you that this object is integrable, so this is essentially this transform matrices. And if we can solve this model using the beta answers, we get all the beta roots for all the eigenstates, then basically we can get basically the eigenvalues of this UF, or even the eigenvalues of Floquet Hamiltonian in terms of the beta root that for each eigenvector. So in the sense that we solved the spectrum of Floquet Hamiltonian, which is very non-local actually. And here you can see that so this is actually a special case of a conjecture by my collaborator, also by the student Tolia Lotkov, and also Denise and Vladimir. Basically, they conjecture that for any quantum circuit that can be written as exponential of Template-Lieb generator, where no matter what representation, it is integrable, because they constructed explicitly local conserved charges in terms of these generators. And here in the 6 vertex case is a special case. So it's a special case of this conjecture that so we proved partially the conjecture of this work. And here I'd like to see that here you see that here we can think a little bit about the locality of the Floquet Hamiltonian, because so this UF is a product of this R check, and if this object is exponentially small, then of course well we would expect to have maybe a bit local, let's say local. Yeah, so basically we would expect to have local Floquet Hamiltonian. Okay, maybe I made a mistake, because when alpha goes to infinity, this is of order 1. So in principle, we can think of it as some kind of limit. Maybe when alpha is small, this thing will be more local, but when alpha is large, it will be non-local. So what I said before was a bit incorrect. But nonetheless, if you just calculate this expression, you get basically this R check where here is related to this beta, which is I have to remind you that beta is 2 cosh eta, and this alpha is a function of apparently of this period t. So here we can write down basically how this alpha changes. And when alpha is real, so basically we know that this H1 and H2, both of them are Hermitian. Of course, this UF is always unitary, and this HF is also always Hermitian. If T is a real number, normally we consider a real time. And in this case, this anisotropy parameter delta is larger than 1, where delta is cosh eta. However, if we consider eta to be purely imaginary, or delta smaller than 1, both H1 and H2, they are not Hermitian because of this imaginary boundary magnetic field. And in this case, we also know that basically this UF is not unitary, strictly speaking. However, in this case, we can plot all this. So basically, this plot is a demonstration of what is real and imaginary part of this alpha. And we see that, for some value of eta, this imaginary part of alpha experience a jump. So basically, there are one part, so this part where this alpha is always real, and for the other part where the imaginary part is pi over 2. And actually for this part, from beta andas, we can show that all the spectrums are real. So there are some statements that from the eigenvalues of the beta equation, the beta roots, eigenvalues of the transform matrices, to get that the spectrum of UF is unimodular. So which means it's on a unit circle, so it's so the eigenvalues are modular to 1, which means eigenvalues of Floquet Hamiltonian is always real. However, for this regime, the argument doesn't work. So instead we did some numerics. We studied this system using, like, let's say, very small system using exact diagonalization, where we find that the spectrum of this UF is not always unimodular anymore, or in a sense that the imaginary part of eigenvalues of HF is not always 0 anymore. And in order to understand this, we would like to introduce this anti-unitary symmetry of this model. So normally people study the PT symmetric Hamiltonian when the Hamiltonian is non-Hermitian. Okay, in our case, it's not really the typical PT symmetry one, but it's also we need to add a little bit, add one more element, which is shown here. So P is the parity reverse, so parity inversion. So if you're acting on, if you're acting on basically on this P operator, we change the operator at side M to L minus M plus 1. And this time reversal symmetry here, it changes some operator to its complex conjugate. So it's not Hermitian conjugate. It's not Hermitian conjugate. So basically, it's Hermitian conjugate without transpose. And of course, we also have the translation. As I said, if you act on translation operator, it just translates your operator by one side. So together, let's see this operator A. It's anti-unitary because of basically of this time reversal symmetry. And there, okay, I will not show you how, but you can really prove that HF commutes with A actually for both cases. So for both cases, it commutes, and A squared is 1. And in this case, so here, okay. First of all, here I only consider the case where delta is smaller than 1 or eta is purely imaginary. So just to stress this point. And in this case, we already know that HF does not commute with, is not the same as HF dagger, and it commutes with this anti-unitary symmetry. So assume that we have an eigenstate that's so with eigenvalue E. So because this symmetry is anti-unitary, this state psi might not be an eigenstate of operator A. Let's assume that if it is, then it's very easy to show that any anti-unitary operator, if A squared is 1, then basically the eigenvalues has to just be a U1 phase. And in this case, we can easily show that basically, so this eigenvalues of the Floquet Hamiltonian in this case is always real. So this E equals to its conjugate. However, if this A acting on psi is a new state phi, which is not proportional to psi, then basically in this case we cannot say that this E is always real. Instead, we will have a spectrum that's in the form of complex conjugate pairs, because you can see that the eigenvalues of phi with respect to this HF is just E bar. So if, let's see, for any eigenvalues psi, that is eigenvalues of HF, is eigenstate of operator A, then we can see that this Floquet Hamiltonian has real spectrum. And in this case, we also see that it's this anti-unitary symmetric, or I call it GPT symmetric. However, if there exists even just one, okay, in this case, there has to be at least two. Well, if it exists at least two psi that basically that are not eigenstates of A, then we see that this symmetry is spontaneously broken because well, this HF still commutes with A. And here we see that, okay, the phase I define here is a little bit different from the phase that's defined for, let's say, for Hamiltonian, because first of all, I'm talking about not only about the ground state, but I'm talking about the entire spectrum. I'm talking about all the excited states. And also, one nice thing about it is that we don't need to take some dynamic limit to observe the phase transition. Actually, the phase transition, it exists for any finite system size, which is quite remarkable because it's a little bit like Li Yang's theory of phase transition. So basically, we do not need any assumption on basically on the system size. And with that being said, we can check some numerical results and try to see what is happening. And we can actually draw a phase diagram where basically, so this beta t, you can see that basically from previous slides, we can see that this beta t is defined up to some integer of 2 pi. And moreover, this gamma here is just the imaginary part of this beta. Also here, sorry, I should write it here. It's actually pi. Yes. And what we find out is that basically this dashed line here denotes the transition between one phase which is GPT symmetric, namely with the real spectrum, and the other one which is spontaneously broken with a complex conjugate pair spectrum. This transition exactly happens when this 2 pi this pi over 2 jump happens. And this actually we check it for system size. Okay, here I always assume that system size is even size because my quantum circuit is acting on basically on 2 sides. And in that case, well, basically the phase transition happens for any system size that's even. However, so this is not the end of the story because, well, if you consider this eta to be at some root of unity, actually at this phase transition point, the spectrum of this UF, it's very interesting. It starts to distribute more or less only on certain root of unity that's related to, first of all, to this integer here L2, as well as to the system size L. But this I will not spend more time on it. So maybe if you're interested, you can see it from our paper in the near future. And with that being said, I would like to conclude tonight's talk. So first of all, I told you about the Floquet integrability, basically constructed from we Baxterize it into some staggered vertex models. And the construction is very general. It works for any Yang-Baxter equation that you like. And also, in principle, it also can be extended to the quantum cellular, sorry, there's a typo here, cellular automaton, where basically your operator is not acting on two sides, but acting on three sides. But there are some recent paper by Balázs Polcskai and his collaborators where they basically propose a similar idea to construct some kind of a staggered vertex models. And then I show you the example of 6 vertex model or XXZ chain, where we prove partially some conjecture on the Floquet integrability of Tempe-Lieb algebra by Denis and Vladimir. And also there's the anti-unitary symmetry breaking, which works without taking some dynamic limit for finite system size, and this very interesting phase diagram that looks like a diamond. And here what I didn't see is that you can also study the spectrum directly from beta-andas, or you can construct the so-called the Baxter's Q operator for this staggered 6 vertex model, which actually also had some very interesting features as root of unity, as in many other cases. But this is not end of the story. Of course, there are many things that I haven't had time to really study. For example, how does dynamics of this of some kind of quantum quench or from this circuit or Floquet dynamics that's integrable, can we really obtain some exact result like similar to the so-called quench action approach for the homogeneous 6 vertex model, and whether there are some different universality class about what I'm really thinking about is about transport problem for this circuit or for this Floquet dynamic, because we already see that basically the usual dynamics that we consider is the limit when this Trotterisation parameter goes to 0. But when it's of order 1, I have some intuition that in principle it should modify the transport property, which would be very interesting to understand in the future. And thank you very much for your attention.
Thank you for a very nice talk.
Thanks.
You're on time as well, so this leaves us good enough time for questions. So I always encourage the students first, if you have any questions. So please raise your hand or speak up. People are a bit shy on Zoom for some reason.
I'm not a student, but may I go in?
Sure.
Yes, Yvan, please.
Thank you. Would you come back on page 13 of your slides?
Okay.
So it's more of a comment only to make sure that I understood.
Okay.
So if I look at your Floquet operator UF,
yes.
Each of the exponentials can be computed explicitly, right? Because the square of all the e's are themselves up to beta. So all these exponentials. Yeah, and it's
only actually on 2 spins. Yeah. So it's very simple. Mm-hmm.
Yeah. So each of these exponential is the identity plus a factor times the EM.
Precisely.
Okay.
Yes.
So if you take in each of the products all the EM, you do generate what's drawn in the diagrammatic version of the affine temporally, the creation of non-contractible loops, which is indeed the worst non-local operator possible. So I do agree with your the fact that your UF is non-local because of this term. Do you agree with what
I
I've
agree
said?
with you completely. Yes, that's
Okay,
indeed a better way to visualize it. Yes.
Okay,
or if you're a bit, let's say, pragmatic like me, so you do the calculation, you will see that indeed it's non-local. Yes. So it couples actually terms basically, lots of terms together. So yeah, but indeed what you said is correct. Yes. Okay. There are terms that's kind of non-contractible loops if you think about graphs, I think. Yeah.
And when you, at the beginning, I think around page 7, you made an argument on time, splitting the periodic capital T into T1 and T2, and yeah, that's the page. So the argument is on time, but at the bottom it has become on space, essentially, where you split H1 and H2. And it's clear when you did the 6 vertex model, because you see that your H1 acts only on the even interaction and H2 only on the other, vice versa. But the passage from time being acting on H1 and H2 to the argument on space can work only if your H1 and H2 has this miraculous property of being split the way it was in your example, right?
That's correct. So in general, of course, these two also are going to be monstrous objects in principle. But here, as I said, I assume that this Hamiltonian is in terms of local terms, local operators, and this H1, H2, I split it into, let's say, more or less like in the 6 vertex example, and then I can get this nice circuit. But this is, of course, not necessary. You can choose a different partition of this H1, H2, where you would end up with very complicated objects in general. And also, in addition, I would like to I forgot to make this comment that here it says I use T1 and T2, but in the later example, it is only integrable, basically when this T, where is it?
The two are equals, right?
Yeah, exactly. When the two are equal. When they are not equal, in fact, if you have one is minus alpha, the other is minus beta, it does not commute. So it becomes non-integrable. So it will no longer commute with this, let's say, this staggered transform matrix. Yeah. So very important is that this parameter has to be the same. Yeah. So basically, this T has to be the same. Yeah.
Is there a way to enlarge U of T to have a spectral parameter, like to embed invent a new operator that would depend on the spectral parameter, and whose value at 0 for the spectral parameter would be your UF? So you would have a whole family of operators.
Yeah, I understand. Yeah, that's a very good question, because in principle, what people would call Baxterisation is exactly what you were saying. You start with something without spectral parameter, and then you upgrade it into something with a for spectral parameter. But here it's not very, so it's a bit rigid, because I have a very good physical intuition what this UF is. So instead, I just, okay, now I kind of come back to it. I just kind of, I can construct, in principle, there should be something maybe here instead of 0, it can be U, maybe. But then I don't know how this, so in principle, this will look more complicated. So in principle, one can do that, of course, because, this is just, this is just a theorem that this UF is this object when the spectral parameter is 0. But in principle, you can put here, I don't know, a U, and then you would get some other object. But if you do that, then why not just consider the T of U, right? I mean, yeah. So so honestly, I do not know how exactly it will look like, but it does not forbid us to, for example, put a U here.
Thank you for the talk and your answers.
All right. So do we have other questions? I have questions. 1, 2, 3. Okay. I'm free to ask my question. So can you expand on this quantum cellular automata extension you were mentioning at the end? You were saying
yes,
this
yes,
would have.
of course.
So what exactly do you
basically,
mean by quantum cellular automata? First.
yeah. So so basically, of course, there's a cellular automaton which is studied classically. So
Yes.
basically, so there are some kind of some map that you start with some classical configurations and then you update using some rules. So the quantum cellular automaton is, instead of updating some classical configurations, you can think of that as some let's say some some quantum initial state, and then you update it. So usually in this case you update it not with circuits like this, so where you update like two sides, but instead what you do is you update three sides, something like this, and then you have some because classical cellular automaton, you need to update, let's say you need to take three configurations to update another one. So that's why the quantum version of it also involves with some circuits that involve with three sides. And in that case, so of course this formalism that I constructed will not work, but there's a more general framework that has been proposed by other people, where you can also embed similar integrability to it.
But so it's just a quantum circuit where you act on clusters of three sites.
Yes, so three sites is because the classical one you update with one side with neighboring three sides. Usually, that's the simplest rule. So that's why in the quantum case you would have a circuit with, let's say, three legs instead of
can I
six
comment,
legs.
excuse me?
Sure.
Excuse me, can I comment just on this? Because quantum cellular automaton, actually also the Trotterisation, which has two-side update rule, can be rewritten and interpreted as a three-side update rule, in a sense, if you correctly shift our matrices across. And a paradigmatic example is Hirota equation. Basically, it's a Trotterisation of quantum Volterra model, but the dynamical equation that you can write can be interpreted as an update of three sides. This is, okay, it's not obvious, but if you look at Fadieus' paper on Hirota equation, I think it will be clear. Maybe we can talk at some other point about this. But even the two-side update rule can be interpreted as a cellular automaton in a way you defined it. So
okay, that's very interesting. I'm not an expert on this. So yeah, thank you, Leonard, for explaining
this. Is clear in the light cone coordinates, actually, on the lattice that is shifted for 45 degrees, if you wish. Okay,
yeah,
sorry.
So yeah, what some people call it light cone pattern, which is here. Yeah, so in principle, the framework that works for kind of this kind of circuits can be updated into more complicated ones. So that's what I call, I use quotation mark quantum cellular automaton. But well, in principle, you can have a more complicated circuit that can be embedded also into integrability. But there you need a bit more complicated R matrix instead of the R matrix that's acting on basically on two sides. So you need
And people have studied those cases with clusters of three or more sides being acted on these quantum circuits using integrability, or not?
Yes, very recently. So of course, first of all, it has been the most famous one is so-called Rule 54. That has been studied by the group of Tomasz Prosen and which also many other people, where they have understood very well, and it itself is also integrable. But more framework point of view, most recently has been kind of proposed by Balázs Polsky and his collaborators, where they present somehow similar construction. That's also in my idea, it can also be, in principle, can be written as something like that. Yeah. But of course, I think they didn't write it explicitly. But in principle, one can do that, I think.
And in this game, to what extent does the choice for the initial state matter? You know, your seed state in which you're doing the circuit. Are you free to choose almost anything you want, or you know, integrability will also restrict the seed state strongly?
So that's a fantastic question. Actually, as we already know from just doing quantum quench, just not with the circuit, just with the integrable systems, we learned that not all the initial states are actually integrable. Namely, some initial states we might not get a very simple dynamics, even though the Hamiltonian is integrable. So there are some initial states such as a Miao state or some kind of matrix product state that has been proved rigorously that using integrability one can study the relaxation exactly. And in this case, I presume it's very similar. So we are so basically from beta ansatz we also get so from beta ansatz of this staggered transform matrix, I would also expect to have some kind of a determinantal formula for the overlap between all the eigenstates, so-called beta states, with certain type of initial states. And only those type of initial states you can get nice analytic exact results. But generically, of course, one still need to rely on simulation. But it's not the end of the story because, well, there are also hydrodynamics that we can use. So, okay, maybe I'm not sure, maybe the state-of-the-art, I don't know, people have already studied very well about the hydrodynamics, maybe they have of this kind of circuit. But with, let's say, initial state that's inhomogeneous, we can use, you know, hydrodynamics as a very good approximation to study the transport problem, for example. So, so the answer to your question is, generically, we don't expect any initial states can be nicely solved. But there are some. But if we are using, let's say, hydrodynamics, we can study a bit more generic case.
Yeah, I guess you can even study mixed states. You use hydrodynamics like that, or you cannot, or it has to be a pure state initially.
I think if you really think about the relaxation, well, there's this hypothesis to say that it should relax to the so-called generalized Gibbs ensemble. There, in principle, you're not restricted to pure state, because well, if you really believe in that, it will kind of generalize, summarize. Then the only thing that you concern is just to calculate all the charges. So there you don't need to be restricted to pure state. But if you want exact result, you want correlation function that works for any, you know, any let's say size, whatever. There you really need to start with some special pure state. But maybe some mixed state could also work. I'm not sure.
Yeah, exactly. I mean, if you have a family of pure states, you can probably have some classical mixture.
Yeah, if you just have simple like sum over two pure states, maybe yes.
Yeah.
Yeah. So some ensemble that's simple enough. I believe it could also be possible.
Yeah. Okay. Thank you. Do we have other questions? Okay, well, I think we've kept you long enough. So thank you again for the nice seminar.
Yeah.
Thanks for answering the questions.
Yeah, thank you. Thank you for having me virtually in Montreal.